Morning. Okay, thank you, Cloud Person. So good afternoon, good morning, I should say. So today we're gonna continue on, hopefully do the balance of our material on networking. And then in the afternoon session, we're gonna have opportunity to build the circuit that was on written exam number 1. But before we begin, project number 4.5, due Sunday, 13th of March, is to enjoy your spring break, right? And so this goes back a long way. I remember when I was an undergrad, and folks in Stochastic have heard this, so those who haven't been in Stochastic aren't gonna know this. When I was an undergrad, I remember we got tons of homework over Thanksgiving break, and rather than enjoying the festivities with family, which is really important to my family, I had to sit aside someplace in the basement and do my homework. And so my mother was very, very off-put by that and said, I'm gonna call your professor and talk to him. And I begged her, please, I want to be invited back into class. Do not call my professor and say what you have to say to this person. And so I vowed then one day, someday, if I ever become a professor, darn it, I'm not gonna assign homework over break. And I maintain that. So your break, at least from my class's perspective, is yours to enjoy. All right, so hopefully one day you all become faculty and continue the tradition and just say, I remember Holness did that way back when. All right, so why don't we get started? Shameless plug again. I have a YouTube playlist for an entire semester's coverage, modern treatment of computer networking, if that's of interest to you, since many of you have not taken computer networking class. So why don't we continue on where we left off? We talked about the client-server implementation for the reliable service TCP. And with this, in this figure, this protocol type diagram, we have a bunch of clients and we have a round trip and a response to establish the so-called connection. And once that connection is established, you get something called a connection socket. And it's this connection socket that abstracts the bidirectional communication between the client and the server. Any questions about this? No questions? No? All right. And so let's continue on with a Python example for a reliable service, transport service for the socket implementation. And here we depict Python code for the client's role, and we'll actually get a chance to do this both on the Raspberry Pi in Python, as well as on the Arduino before that in Sketch. And so we start out, and when we create our client, we need to know two things. We need to know the address of the server, but we also need to know the port number associated with the server. And so with this, we start out, we create our socket, and you notice the difference here. The second parameter, when we create the socket, says sock stream. In contrast to Unity, it's a sock dgram. Sock stream is the reliable transport, and you as the application writer have to tell your transport layer which service you're intending to use, the reliable service, TCP, or the unreliable service, UDP. So once we make this, initiate this socket, and that could be instantiating an object or calling an API, depending on how it's implemented in your language of choice, you then connect. Now in Java, you instantiate the socket with the address of the server and the port number, and it does that work for you. But here in a procedural language like Python or C, you're gonna call APIs to do this for each of the steps. And two of the pieces of information you notice when you have this connection call, it specifies the name of the server, that's the host name or the IP address, and you also have the port number. Those two pieces of information are needed by the client, and underneath the covers, when you make this connect request, this round trip for establishing the resources on the server is made on your behalf. And so once this connect request unblocks and continues, it means that the server either gets an error message or an exception, or it returns okay. And now you can assume, you being the client, that the server can keep up its part of the bargain for the reliable communication. Okay, so then here, we get the piece of data that the client wants to send. And this is a trivial example. The client sends text that you type at the command line, and then the server capitalizes it and returns that capitalized version as a response. And so you get your input from the command line, you send it, and then the client then goes to do a receive on the socket. And when you do a receive, you have to specify in most languages the size of the buffer that's going to hold that. In something like C++, or C rather, you have a pointer to a buffer that you created ahead of time. In other languages like Python, you give it a size specification, and the runtime in Python manages that buffering for you. Okay, any questions about this? Questions? No. All right. And then, of course, once you're done, you take that response from the server, you being the client, and then you do something with it, and you go ahead and close the socket on the client side when you're done with this communication. And this is the server. And in the reliable transport, TCP, the server implementation is a bit different from UDP. You start out and you choose a port number on the machine that you're running your server on. And you also create your socket. That doesn't change. And so here, AFINet is IP version 4, sock stream is the reliable transport TCP. And then this other stuff, bind it. And so in the server side part, programmatically, for TCP reliable service, transport service, you have to associate your socket with your port number, because that's the glue that gives the transport layer the information necessary to know which process originated this data in the outbound direction and which process should this data be delivered to on the inbound direction or in the inbound direction. So after creating this so-called server socket, it goes ahead and binds the server socket to the port number. Now, two things can happen. Either the bind works, and now that particular process, that door, magical door we talked about before, is associated in this case with port number 12,000, or it says someone's already using that port, right? And it is recommended if you write your own server programs that you do not use port number 0 through 1024. Those are the so-called reserved port numbers, and things like HTTP, things like your file system and other system services assume those low number port numbers, right? You might break something on a system that's networked if you try to use one of those port numbers. All right, so then the next thing is that you listen. The server socket, its whole responsibility is to wait for incoming requests. So imagine someone waiting by the phone for it to ring, and the moment that phone rings, you pick it up, and it says, "Can I speak with John," for example, just made it up, and then you hand the phone to John. And that's essentially what your server socket does. So on the server side, for the reliable transport, TCP, you have two sockets in play. You have a server socket that waits for incoming requests, and then when an incoming request is connected to a client that's trying to connect to this server, another socket is created, a so-called connection socket. Running out of moisture, didn't drink enough water this morning. A connection socket. And that connection socket is the door for the communication between the server to that particular client who has been granted a connection. So we have our server socket, we bind it to the port number, go ahead and listen for incoming connections, and then in a tight while loop, we listen for the particular connection. And so this server socket accept call is a blocking call typically, unless you're using something called asynchronous IO. And when this accept call returns, you notice one of the pieces of information returned is a so-called connection socket. Watch that come back on. Is a so-called connection socket and the address of the thing that's connecting to you. Because the client knows its own IP address, and you notice the client didn't have to specify its address. That was part of the payload inserted by the runtime. And I'll talk a little bit about TCP endpoints in a few slides. And so once you accept, you get this connection socket, and whenever the server receives information from the client and sends back a response to the client, it does it through that particular connection socket. And so each time a new client comes along, and imagine like a web server, you have 100 people or 1,000 people that are connecting to a web server, there's a connection socket somewhere in that server process for that particular web server. And that's part of this idea about these resources that we talked about. Underlying each one of these connection sockets are buffers, timers, and a whole host of other things that implement all of the responsibility on the server side for this reliable communication. Okay, any questions about this? No? All right. So then through the connection socket, the server receives whatever protocol message was sent to it. It makes sense of it, does some work. In this case, it's just converting to uppercase. It's trivial, but it still works. And then through the connection socket, it sends a response back to the client, and then it closes the socket if it's the end of the communication. Okay? And in a high-performance server implementation, it's really, really important to make this part fast. And in modern implementations, you're going to use threading. Have you done threading? Threading? No? But maybe I'll save that for another time. All right. So you'll use something called threading, and modern server implementations have message queues. And so you can keep with message queues this loop very, very tight. And the only thing it does is takes requests and puts it on a queue, and then you have a bunch of other workers picking those requests off the queue and doing something and interacting with the client. I'll talk about that a little bit from a good engineering practice standpoint after the break. All right, any questions? No questions? All right. All right, so let's take a look at how the runtime for the transport layer distinguishes between one end-to-end channel communication and another. And so we have some pieces of information that we talked about. We talked about the network interface and the IP address. It identifies uniquely across the network, the particular network card or interface. And then we also have the port number, and the port number identifies the socket. And so here we have a number of connections. We have some server in the middle, and we have some other machines on the left and the right. And in this diagram, this golden rectangle, that's the socket depiction. And you'll see some inbound and outbound arrows. And let's imagine this machine in the center is a server, and we have a bunch of processes, P1 and P2, running on it. So we have a client that comes along here, process P3 on the left, your left, and a client that comes along, P4. You might be attaching to www.rp.edu, for example. And when we have these connections, it's the socket on the outbound side, if we were going from process P1 outbound to process P3, process P1 in the transport layer through the socket, that particular message is stamped with the port number in the transport layer. And that's how the transport layer can identify, yes, it was P1 that originated this message. And that's useful when the application in the other direction, it sends information to process P1. How does it know which process it's going to be delivered to in the operating system runtime? It knows because it says, all right, well, I want to send it to port number 12,000, for example. And so when that datagram comes off the network, through the network layer, to the transport layer, it unpacks that port number and says, aha, port number 12,000, that's this socket. And that's how it knows where to deliver that segment or that message payload more correctly when it arrives on the inbound direction. And so two pieces of information are necessary to identify these endpoints in a communication. We need the IP address to identify the network card, the interface, and that's a construct that's meaningful to the network layer. And we also need the port number, and that identifies the process, whether it's inbound or outbound for that data. Any questions about this? All right. And so I'm not going to go over that. This is a schematic for the header information for the transport layer. And we have some other fields that I won't talk about, but most important is the application data payload and these two pieces of information, the source port number and the destination port number. And so each one is 16 bits. That means you have a maximum of 65535 different port numbers, and port numbers 0 through 1024 are typically reserved for things like HTTP, XMPP, and all sorts of other stuff. Any questions? No questions? No? All right. And so when you use UDP, we said UDP is unreliable, but it's really, really fast. It's also called the connectionless service instead of TCP, which is the connection-oriented service. Now, when we had the example last time for sending a datagram via UDP, we saw that each communication when you said send on that socket, it had to include both the host name and the port number. And the reason for that is because there's no establishment of resources. There's no notion of a server socket and a connection socket. And so because of that, with UDP, every time you do a send, you have to tell it where to send it, which interface card, the host name or IP address, and which process, the port number. And that's the case on the server as well as on the client side. Okay. And so we have these pieces of information on the connectionless example. We create our datagram socket, that's a sock dgram in the API, and we associate a port number with each one. And so here in this example, the machine on the left, it has a port number of 9157 associated with the socket bound to process P3. And then on your right, we have this other datagram socket. It's associated with port number 5775, which is this blue that communicates to and from process P4. And so now imagine we have a server in the center, and it's associated in this example with port number 6428 for that socket. So if we were then to send a communication from the machine on the left, process P3, to our server, the source port number would be 9157, and the destination port would be 6428. That's in the outbound direction. But on the inbound direction, if we got back a response from that server, you'll notice those two pieces of information flip. The destination port is now 9157, and the source port for this datagram is 6428. And so this information is needed, and each packet in UDP is specifically stamped with the port number, source port, destination port, as well as the host name. Any questions? Does that make sense? No. All right. And so this is just a question for you. You can see it, the source port, destination port switches from P1 going to P4. Source is port 6428. Destination is port 5775. And they reverse when the message is going in the opposite direction. And so what happens with our connection-oriented service, this TCP, that consists on the server side of a server socket and a so-called connection socket? Now, this pipe, as it were, is bidirectional, and that connection socket, we said, is specific to a communication with a single client in this client-server communication. And so we have four pieces of information: the source and destination IP address, and the source and destination port number. And every single channel of communication in TCP is uniquely identified by this four tuple. And that's exactly what the underlying runtime uses to decide where should I direct this datagram when it comes into the machine. And so here, in this example, one of the differences between this and the previous diagram that we displayed is you notice these edges are bidirectional, right? They're bidirectional because it represents the connection socket, because recall, once you establish the connection, you use the same connection socket using the server for communicating with the client or getting information that requests from the client. And so you notice that always drives me up because, anyways. So you notice here, for this communication, we have our machine on the left, our machine on the right, and then we have a server, for example, in the middle. And so here is not atypical, it's very mundane to have multiple clients connecting to the same server. So how does that server machine, that runtime for the networking stack, how does it know with all these datagrams coming in, to whom do I send this incoming message? And so for this connection between the machine on the left-hand side and our server, we have the source IP, and let's imagine this machine is IP address A. We have IP address B, we have IP address C. And so here, to identify this bidirectional communication, we have the source IP, and port is B80, A9157. We have, now it's flipped, but it's the same four tuple. We have A9157, B80. And so this four tuple identifies uniquely this particular channel of communication. So when a datagram arrives from physical up through link, up through network, hits the transport layer goes, gosh, well, who's associated with this? Let me look up what is the source destination IP, What is the source destination port number? Aha, that matches this particular socket. Let me forward that datagram up through that socket in the runtime implementation. Okay, any questions? All right, so sometimes when you connect to a web server, you get this weird message that it doesn't have resources, right? Every once in a while, especially when something, is emerging and it's new and a lot of people are converging onto a certain website. And that's usually because it ran out of the resources in order to support all of these underlying sockets on the server side. And when you want to scale this up, what ends up happening is you have this dispatcher that sits there in front of all the servers that you have in your data center. It gets a request and it performs some calculation and says, well, which is the best server among the thousands of server instances in the data center to which to forward this request. And so that scalability is implemented as a cluster through what's called a cluster controller. Sometimes you use DNS to do it, but with DNS, that's typically for static or relatively static content and not so much on application work sets like you'd see in like AWS and Amazon and things like that. Okay, questions? No? All right. So UDP does not have any of these reliability guarantees. And so you might ask, why in the world have a UDP? Well, there are applications where speed matters, in particular, things like video. And there are other applications where you can tolerate losses, things like streaming audio. And so in these applications, they use UDP because that speed and that loss trade-off is very well managed. But for something like robotic surgery, you'd never use UDP. Because you can't afford to have corruption or to have commands get lost. UDP won't even try to resend things on your behalf should they get lost. It just doesn't deliver. You say, oh, all right, well, what do you do? Okay. So for UDP, in the segment header, in addition to the port numbers, there are some other pieces of information. It'll perform a checksum and reject a message if it detects a certain amount of corruption, but it won't do anything about it, right? TCP will say, this was corrupted. Let me set a timer. And if I don't get back a response, I'm going to resend it. So it ensures for you through a number of actions that this thing that you sent will eventually get delivered as you intended. Okay. And so let's take a look at where I was hoping to spend most of my time today. And that's on the IP address and on the MAC address. And so when you try to identify a machine, in the beginning, it was assumed that each machine would have a single network card. And this connection between the physical link and the host is called an interface. And if you go on the command line and type something like ifconfig, you see a whole bunch of so-called interface names. Those are the names associated with all of your network cards, all of your network interfaces. And so this interface implements the pushing of packets physically on and off of the network, and each interface is uniquely identified by a so-called IP address. And these are some examples of an IP address. We have like 223.1.1.1. Now, when you express an IP address in IP version 4, it's 32 bits, and it's expressed 8 bits at a time as something called a dotted quad. And for this dotted quad, what they do is every 8 bits, they interpret this binary number as the equivalent decimal number, and they write it out in decimal. And so one of the observations that you'll notice here is that this naming of IP addresses is highly stylized. And you notice here the prefix or the uppermost bits, 24 bits, 24 bits of the IP address is 223.1.1 for all the machines on this part of the network, and 223.1.2 on this part, 223.1.3 on the other part. Now that's on purpose. And each one of these hosts that share the same prefix, 223.1. something, those are individual networks, islands of connectivity. And so how these are actually connected in practice is through a device called a switch. And I remember when I was just going into undergrad, switches didn't exist in the same way they do now. You studied different network architectures and ways you connect things on a physical, to the same physical medium. And so there are different ways of connecting devices on the same network. One is a switch if you're wired in modern times, and the other is a wireless access port for Wi-Fi. Now, those on the same network, they're directly reachable to one another without needing a router to store and forward packets from one set of directly connected devices to another directly connected set of devices. And so if we were to remove the interfaces, these machines, they're next to one another, considered adjacent. And all of those adjacent devices are considered to be on the same network. And I'll explain a little bit more about what I mean by that. And so when we look at these addresses, we notice, as I said before, alluded to, that the uppermost bits are the same for a number of machines, and it's those machines that are directly connected to one another, whether or not it's guided media, like a wire, or unguided media, like wireless. And so that uppermost set of bits that are the same for each machine, that's called the network address, or the so-called subnet. And that subnet is what identifies all the machines that are directly connected to one another. And so in this case, we have the 223.1.1 subnet, we have the 223.1.2 subnet, and we have the 223.1.3 subnet. Now that last part, the low order bits in our dotted quad and our 32-bit address, that's the host number. So this is host number 1 on subnet 223.1.1. This is host number 4 on subnet 223.1.1. Likewise, this is host number 9 on subnet 223.1.2. Now those numbers don't have to be sequential. They just have to have the same subnet or the so-called network address. Now, you'll notice also that the router device we talked about, it stores packets and it forwards packets. You notice this router, it has interfaces on multiple networks, on 3 different subnets. That's how the router is able to store and forward, because it sort of straddles between or among multiple networks or multiple subnets. Okay, and so a network, formally defined, are a set of hosts that are directly connected, share the same subnet, and can reach one another without the intervention of a router to store and forward these data grids. Any questions about this? Does that make sense? All right. So when you get a network address, you typically get network addresses for your subnet, and it represents a so-called block of addresses. Now, typically what happens is when you purchase a block of addresses, you're given your subnet in the following way. You have the name of the subnet, 223.1.1, and then you have this number called the subnet mask. And what the subnet mask tells you is how many bits are used to represent the subnet part of your IP address. So in this case, the first 24 bits, which is 8 times 3, the first 3 dotted quads represent the subnet, and then the last 8 bits in our 32-bit address I use to identify the host. And so with this set of networks, you can have 2 to the 8 or 256 many hosts on that particular subnet. Any questions about this? Does that make sense? And so typically what would happen if you want your own network, you go to an ISP, and the ISP owns a block of addresses, and they're leasing to you on a subscription basis some subset of the IP addresses that they have ownership of or that they manage. Okay. So here's a diagram, and one of the questions, how many subnets or networks do you have in this diagram? And the key here is that a subnet is a set or an island of connectivity, as the Rosa-Ross book calls it, and you don't necessarily have to have hosts per se to make it a subnet. And so here we have the 223.1.1 subnet. We have a bunch of hosts there. Here we have the 223.1.7 subnet. We do have machines there, we have this interface for that router, we have this interface for that router, but that particular subnet doesn't have any hosts, no servers, no cell phones, no machines and things like that. But it is still an honest to goodness subnet. We have another subnet here, 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 and here. So it's a total of 6 subnets in this network. Any questions about this? Does that make sense? Now, why would you do this? Well, it's entirely up to you. When you get this connection from your service provider, it's entirely up to you how you organize the so-called topology or geometric layout, so to speak, of your network. It's entirely up to you. And the considerations that you have is where is the traffic going? What traffic is it? And how is that traffic at certain times of the day going to impact the end-to-end data flows for the user base that access your network? Okay, and so in the early days, and this is important history, they didn't think that an individual would have so many connected devices. They thought, and I remember Bill Gates was reading, famously said, you'll never have, what's the IBM? I can't remember. But somebody said you'll never have more than a few dozen computers in the United States. And that was sort of a joke by today's standards. But originally, when they designed the address space for interfaces in IP version 4, they had what they called classes of networks. They had a class A network, class B network, class C network, and so forth. And what that A, B, C, and D represented is which part of this prefix identifies your subnet. And so if you were a so-called class A network, that meant that your subnet mask was 8 bits, and that meant you had 2 to the 24 many hosts on your network. And that was a really large network, but what ended up happening is that quickly we ran out of IP addresses, and more and more devices got connected to the network. And so the solution to that was not to carve it up in 8 bits at a time as the prefix to identify the subnet. The solution was to have arbitrary size subnets. And so this idea of classless interdomain routing, or CIDR, so-called CIDR-ized IP addresses, is what happens today. And what this does is it gives you a hierarchical naming for your IP addresses. And this is literally what routers use when they're trying to do prefix matching to determine what interface a datagram should be forwarded. Any questions about this? And so routers will literally talk to one another using something called router advertisement. And that's how routers know, if I have a destination address that has this prefix, I know I need to send it out that way. So this network address, let's look at the link layer. That's the IP address. And the IP address identifies globally the network interface where this datagram should be pushed. And so we talked in our first module on computer networking, part 1, about the architecture of the internet. And we said we have these devices, whether they're hosts or switches, which I'll talk about very soon in more detail, or routers. Now, the link layer pertains to all of those edges that connect them together, be that unguided media, like wireless, or guided media, like twisted pair copper wire, or fiber optic. Now, a so-called local area network is the term ascribed to all of the devices that are directly connected or reachable to one another without the intervention of a router. And so the responsibility of the link layer, or the data link layer, is to manage the transmission of so-called frames from one device that's directly connected to another device that's directly connected. So the first thing that happens in the communication is that your device locates its router, it's directly connected, that interface, and then the router stores and forwards it across another link layer, or link, or directly, or guided media. All right, I'm jumping ahead in my mind. And so the link layer's responsibility is to manage the sending and receiving of frames, as it's called, or packets, along the links to a directly connected device. Okay, and so in the Pearls Ross book, they like to use lots of human examples, and they have an analogy that talks about you're planning a trip, And the link layer is like that particular leg of your journey. It's what gets you to the directly connected other endpoint. And so the thing that link layer is responsible for, and it does a lot of interesting things. And there are different link layers depending on what sort of physical media you have. So a link layer for fiber optic does different things from link layer for twisted pair copper wire, does different things for a link layer for wireless. Now wireless, of course, in the airwaves, your access point, like this Aruba access point, is not the only thing projecting electromagnetic energy into the environment. You can hear the motors on the HVAC system. That motor is producing really strong electromagnetic fields, and you get a lot of interference. And so one of the things the link layer does, for wireless in particular, is a lot of error detection and a lot of correction of those errors. But in something like fiber optic, you don't really have much of that because there's not a lot of interference inside of that fiber optic strand. And so when you send a message from your source to the destination, it might go, for example, in this room, from your laptop wirelessly to this Aruba Networks router or access point. And then from there, it goes through twisted pair copper wire, and then eventually gets to the backbone for part, and then probably makes its way out by wire. And so for multiple links that you traverse, your hops will consist of different types of physical media, and therefore different link layer concerns are in play. And so just because you have a link layer, it doesn't mean that they're all the same. They're all very different depending on what type of media your datagram encounters. Any questions about this? And so one of the things that the link layer does is implements a type of reliable delivery, but that's only to adjacent nodes on the same media. And for something like wireless, it's spending a lot of its time recovering from errors because you're going to get a lot of noise in wireless. Okay. The link layer also controls the rate of sending. It detects errors. It also corrects a certain category of errors. Is it going to correct an error in a single bit? Probably not. But typically, when you have errors, those errors are bulk. And so you can hear the HVAC system. And whenever you have errors, it's usually a long span of bytes that get corrupted. And so most of these error correction and detection techniques will detect coarse level bit errors, not individual bit errors. Okay. And so you might ask, well, where physically does this link layer exist? Where does it live? Well, it lives in your network card, and some of it is implemented in software, namely the drivers, and some of it is implemented in hardware. Typically, those parts of the link layer that deal with the physical interface, the controller implementation, is done in circuitry because it interfaces with either fiber, wireless, or twisted pair copper wire. But then the rest is typically a driver that is a specialized piece of software buried inside of your operating system or interfacing with your operating system. Now, if you've ever bought a network card, some of them don't even exist as cards. They're a chipset that's affixed to your motherboard. But if you actually buy a physical network card, sometimes you'll notice that network card, it'll work with Linux, Mac, or Windows. Other times, sometimes those network cards will only work with Windows. And in those cases where they're restricted to a particular operating system, that means that they've implemented parts of that, more parts of it in software and not in hardware. But the pure hardware ones are typically the cards that cost a little more, and they'll also work with multiple operating systems. Are there any questions about this? That makes sense? All right. And so we have our sending network card, and we have our receiving network card, and the link layer interfaces with the network layer. The network layer is responsible for getting your datagram from one machine to another machine across the internet. Now, this link layer, it takes this datagram from the network card, and it's responsible for implementing the transmission across the physical media to some directly connected other receiving side. And so important to the link layer is the so-called MAC address, or media access control address, the same MAC address that I asked for your Arduino boards. And where the IP address is 32 bits, the MAC address is quite different, it's 48 bits. And this MAC address is typically written in hexadecimal, And each one of these hex digits represents 4 bits. So we have 8, 8, 8, 8, 8, 8, and it's a total of 48 bits. Now, when you look at the design of a MAC address in something like Wireshark, when you're intersecting packets, you notice that Wireshark knows that this is a particular manufacturer's network card. Now, how it knows that is the first half of your MAC address, it's assigned vendor specific. So if you want to start making network cards, you could absolutely do that. You go to IEEE, Institute for Electrical and Electronic Engineering, and you say, hey, I would like a MAC address number assigned to my company. So they give you a MAC address, and you have a specific upper 6 digits. And then as you stamp out these network cards in a factory somewhere, you can control yourself what these lower bits are, the lower 24 bits are for your network card. Now, these MAC addresses, unlike the IP addresses are globally unique. MAC addresses only have to be unique on the same local network. So what does that mean? It means that if you're a manufacturer and you create a network card, 2 network cards can absolutely have the same MAC address. But you want to make sure maybe you send one to Best Buy in Worcester and the other one goes to Best Buy in Hamburg, Germany, right? You just make sure that it's very unlikely that they're going to coexist on the same physical network at the same time. And so a MAC address must be unique, but it only needs to be unique on the same local network. Does that make sense? Yeah? Any questions? And so here's an example of a MAC address. And if you type ifconfig on your command line, you'll see among all the information the MAC address for your machine, okay, for your network card. And so each adapter on a local area network could be guided or unguided, has a unique MAC address. In this figure, these green boxes represent the network interface, and each is annotated with their MAC address. And so you'll notice they're all unique on this network. And again, you could have some other network with the same MAC address for its network card. And so they have to be unique, and you can think of them as being portable, absolutely. You can take your network card, go to some other city, country, what have you, and it's going to work, provided that your MAC address is unique. Otherwise, you're going to have a lot of issues on your network. And so the question then is, suppose you're on the same network and you want to send a frame to another device on the same network. Well, we know that IP addresses merely identify a host, but if you're sending on the same network to another device, like a router, you have to use the MAC address. And so how do you get the MAC address for some other device that's directly connected if all you know the IP is, if all you know is the IP address? Well, each host has its IP address, and each host, because it's an interface card, has a MAC address. Now, there's a protocol on the link layer called ARP. It stands for Address Resolution Protocol, and it's a broadcast-based method for associating IP addresses, which are known, with MAC addresses, which might not be known. Because as a device, let's say you come to the classroom, you open your laptop, how does the system know that if you want to send data to the router to get off the network or on the network, how does it know how to locate the router's MAC address? And it's this ARP that implements this. So the first thing that happens when you join the network, there's something called Dynamic Host Configuration Protocol, which I won't talk about. And this DHCP, as part of your joining the network when you open your laptop, one of the things it gives you is what's called a default gateway. And the default gateway is the IP address of that so-called first hop router. It's that router that shares an interface with your network. And that's what you're going to use, that router, that default gateway, anytime you want to get packets off of your network or packets onto your network. And so knowing the IP address of your router or any other device on your local network, this ARP is built dynamically, and it's a type of mapping table. Now, in this ARP mapping table, or ARP cache as it's called, there's an entry for an IP address, and there's a corresponding entry for the MAC address associated with that IP address. And there's also some management stuff, so-called time to live field, and that's so that stale records are automatically purged from this ARP page. And as you plug in your machine, once you acquire the default gateway and your IP address through DHCP, it engages in this ARP to dynamically populate this ARP table or ARP cache. And so what happens, there's a special MAC address that no card uses, and it's the broadcast MAC address. It's all ones, or FFFFFFFF. So imagine 48 bits of ones. And when you first join the network, you start broadcasting, and your broadcast is going to be like shouting from the rooftops. Question? Yes, all ones. Yes. I know words. You're shouting from the rooftops. Who has IP address 192.168.1.114? And if your router has that IP address, it's going to answer back by a broadcast. That's my IP address, and this is my MAC address. You then write down that entry in your ARP table. And now, when you want to directly send your frame to your default gateway, you're going to know its MAC address. Any questions about this? No? All right. And ARP is plug and play. You don't have to do anything but plug in your machine or join the network, and it populates your ARP cache for you. And this is something you can absolutely see in Wireshark. You can, there are commands on the command line I can talk about another time to actually take a look at the ARP cache. You can actually see, once you join, all sorts of things start to pop up, like the local printer, right? There are printer protocols for advertising themselves. The router's MAC address and IP address, and all sorts of other things. Any questions? No? And so let's assume you want to send a datagram from host A on the left, your left, to host B on a different network across the internet on your right. Now you know what A's IP address is, that's you know your IP, and you know your MAC address. And every other host on the network has an IP address and a MAC address. Now we know from ARP that A can discover all of the IP address to MAC address mappings for machines on this local network, but it can't do that for machines on a different local network. And so A, when it joined the network, it knew what its default gateway's IP address is. When A joined the network, it said, the HCP told me if I want to get data off this network, I should use IP address 111.111.111.110, and that's bootstrapped by something called DHCP, Dynamic Host Configuration Protocol. So now, when A engages in ARP, it says, what is the MAC address for this IP address that is my default gateway? And it gets the MAC address E6E90017BB4B, which is the MAC address that the router has for its interface that it shares with this network on the left-hand side of the board. Does that make sense? Any questions? And so now that A knows the MAC address associated with the default gateway, it has an IP address that it has for B, like www.clarku.edu. You can coerce that into an IP address. So A then sends a datagram down through its stack, and its source IP address is A's IP address. The destination IP address is the IP address for B all the way across the internet. So now what does A do? Well, it knows that if it wants to send something to that destination address, it knows it has to send it to its default gateway. So it initiates in its link layer, which is Ethernet in this case. It says, well, my source MAC address, so that's A's MAC address. The destination MAC address is going to be the MAC address associated with that interface of its default gateway. So it sends that into its link layer. And when the router R sees that destination MAC address, it says, hey, wait a minute, that's my MAC address. If it's my MAC address, I'm going to take that frame off the network and bring it into memory. And so this router knows this message is intended for it. It then takes it off the link layer from the physical media. It sends it up to the network layer. And it says, oh, wait a minute. The destination IP address is this 222.232, etc. So then it says, okay, well, what is the prefix for this particular IP address? I look up in my routing table, and I notice that for a particular prefix for this destination, I'm going to send it out this interface, the interface I share with the 222 network. And so the router then sends it back down the stack, and it restamps it with the MAC address that it shares with this other network as the source MAC address, and the destination MAC address is now going to be the destination for host B from a MAC address standpoint. Now, you might ask, well, how did this router know the MAC address for host B? Well, this network, all these devices are engaging in ARP. And so when B joined the network, it got a default gateway. So B knows what the router is. And the router on the 222 network also engages in ARP. So when B joined via DHCP, it said, oh, wait a minute, what's the MAC address for 222.222, which is B's IP address? And then B answered with its MAC. And so all the machines on a single network know what the MAC address is for all the other machines on that same network. So this router knows what the MAC address is for host B. It knows the destination address warrants this datagram being forwarded out this port for the 222 network. So then it pushes that datagram into the link layer and into the physical layer. And when this datagram is on the link layer, host B says, oh, wait a minute, that destination MAC address, that's my MAC address. It pulls that frame into memory, and it unpacks it and delivers that message to the application layer above. Okay. Any questions about this? That makes sense? And it gets delivered. All right. And so when the early days, I remember this, I was just out of high school, in the earlier days of networking, you had to consider how you physically attach the machines to one another. And there were different so-called physical topologies that were employed for directly connected machines to one another. One was bus-based, and I remember that. And these network interface cards would physically tap in to the same conductor, right? And I remember they had this device that bore a hole and actually connect them together. It was interesting. And then something called the hub and spoke topology arose. And this hub and spoke topology had a single machine on the so-called spoke. And then in the center, they were connected together at a tie point in a conductor. Now, over time, this hub and spoke grew into what was called a star topology. And a device arose called a switch. And the switch is a link layer device that is invisible to all the data flows for the machines attached to it. But what the switch does, it performs what's called selective forwarding. And the switch's responsibility is to forward link layer frames in a way that you don't get collisions. Now, a collision is that term referred to when two different nodes, remember they're directly connected, when they're both trying to communicate on the network. It's very cold. When they're both trying to communicate on the same network. If you have two devices trying to put signal energy on the same conductor, what's going to happen? It's going to interfere with one another. If you're sending a sine wave and I'm sending a sine wave, the two are going to mix and you're going to get a resulting sine wave, which is some combination of the two. And that means the data is not going to be what we both intended. And so what the switch does is it takes each one of these signal energies from each spoke and it forwards it in a way that you don't get these collisions. Now, what does that mean as a resulting attribute? Is that it makes this topology much, much faster. Because part of what you have to detect in the link layer is when two or more hosts are trying to engage in communication. And what typically used to happen is that you detect, wait a minute, there's too much signal energy to represent one set of communication. Let me go ahead and back off pause for a little bit, and then try again. Now, if people are pausing for a little bit and trying again, it means you're not getting full use of the communication bandwidth. And so this elimination of collisions gives you more use of the bandwidth, which is why you hear terminology like switch to Ethernet is much, much faster. And so right now, the standard, at least for local area networks, is gigabit switch Ethernet. And the switched part is this device called a link layer switch, which eliminates these collisions, and therefore you get much, much faster use of the available bandwidth. Okay, any questions about this? All right, so this link layer switch takes an active role and it eliminates this CMSA-CD, carrier sense multiple access collision detect. And if you can reduce the collisions, you can increase the throughput for the communication. And the switch is plug and play. It'll populate itself with information that it's going to use to identify MAC addresses and the connection that MAC address exists on in order to forward these frames instead of causing collisions. And so in this example, we have a so-called star topology, a switched Ethernet, and we have on each spoke a host, and each host has a MAC address. And so we have MAC address A, MAC address A prime, B, B prime, and so forth. And you'll notice here, because you exist on a single spoke, a single host does, you're the only one putting signal energy on that particular conductive pathway. Now, we also have a set of ports or interfaces on our link layer switch. And so if we were going to have collisions, a collision would be if A is sending a message to A prime, and at the same time, for example, B is sending a frame to B prime on the same medium. Now, what the switch will do is do this forwarding so that you don't get collisions. And we know we don't get a collision on a spoke because only a single host is on that spoke. It's once you get to the tie point in the middle that you get these collisions. And so one of the questions then is if host A is sending to A prime, and then A prime might be sending a response back to host with MAC address A, how does the switch know at which spoke to send this frame? Well, it builds a so-called forwarding table with something called selective forward. And I'll explain in a moment what that means. And so each switch has a table entry, the switch and every switch. And switches, when you buy them, you can buy a small one at Best Buy for like $30, 4-port switch. But if you have rack mounted, they'll come in denominations of out 2, 16-port switch, 32-port switch, and so forth. And some of these switches you can chain together in a virtual way to aggregate them with one another. And so here we have 6 interfaces, and these entries are dynamically created as a consequence of the BOSIN, the message traffic that flows across the switch. Now, let's say we have these MAC addresses on a so-called 6-port switch. And let's say link layer or host A, or network interface A, it wants to send a frame to the host of MAC address A prime. Now, these are MAC addresses, not IP addresses. And so the source MAC address is A, the destination MAC address is A prime. So it sends it down its spoke, it hits the switch. Now, the first thing that happens, the switch says, aha, well, some host with source MAC address A originated this message, and this message arrived on interface 1. And so because it arrived from interface 1, and the source of this frame had MAC address A, I know that MAC address A is reachable on port 1. So it populates its table with an entry. If I want to reach MAC address A, use interface 1. And then it has a time to live field so that this thing will clean itself up if host A is no longer there. Any questions about this? That makes sense? Okay, so now this switch needs to forward this frame, but it doesn't know where host with MAC address A prime exists. It has no idea. So what can it do? It has to broadcast. So now, if it doesn't have an entry, doesn't know where to send this frame, if it wants to reach MAC address A prime, it goes ahead and it sends it out every single interface, except that port number that it arrived from. Because why would you forward from A back to itself, right? And so the protocol or the schema implemented is depicted here algorithmically, the so-called selective filtering approach. So you start out, if you have a frame coming inbound on a port, you record a table entry to say that source MAC address is reachable on that port that it arrived on. Then, when you see the destination MAC address, you index the MAC address forwarding table. And if you have an entry, you go ahead and you forward it out that port number to the destination MAC address. If you don't have an entry, then you go ahead and flood. You just send it out every single interface, every port, except the one that it arrived on. So let's take a look at this in action, so-called self-learning. So A, as we said, where we left off, it sends a MAC a frame and it wants to send it to a host with MAC address A prime. So it hits the switch and it arrives on port 1 on the switch. So the switch populates its MAC forwarding table. If I want to reach A, I use interface 1, sets a time to live. So now this switch does not looks up MAC address A prime. It doesn't have an entry. There's nowhere to send it. So it does the flooding. It does the flooding. It sends out a copy to each one of these interfaces, these ports, except for the one it arrived on. So now what happens, all of these link layers, C prime, B prime, A prime, C, and B, they get this frame. When they look at the destination MAC address, they say, whoa, that's not mine, that's not mine, that's not mine, except for host A, says, wait a minute, that's my MAC address in the destination field. So that message is intended for me. So it pulls it into its memory. And if A wants to communicate with A prime, usually at some point, principle of gossip, A prime is going to want to communicate with A. So now let's say this is a client server application. A is the client, sends a message to A prime, and then A prime wants to send a message back to A, right? And so now A prime sends its message to the switch, and it arrives in this case on port 4. When the switch sees this message, it says the source of this communication, the source MAC address is A prime. So and it arrived on port 4. So let me record. If I want to reach A prime, I use interface or port 4, and I set a time to live. So now it goes ahead and it says, okay, that was the source MAC address. The destination was what? It was A. It looks up in the table, aha, there's an entry there for MAC address A, forwarded out port 1. So now instead of flooding, because it has an entry in the MAC forwarding table, it's going to go ahead and now forward that with specificity out port 1 to A. Now this happens for every set of endpoints that communicate. And over time, this MAC address table, once it's fully populated, there are no collisions and there's no flooding. And so it kind of warms up very, very quickly, just as a consequence of your communicating, and you don't have to do anything for it. Now, the important thing here to remember is from the standpoint of the hosts, this switch is invisible. They don't even know it exists. It's just something that happens for you to implement this hub and spoke topology without collisions. And it's entirely done by this link layer switch, a so-called layer 2 device, because it traffics in MAC addresses, which is a layer 2 construct, i.e. the link layer. Any questions about this? And so the so-called self-learning that the switch is engaging, you can connect switches to other switches, right? It's pass-through device from the standpoint of the host. And so in this configuration, this flooding and this recording in the MAC table, it populates for arbitrary topologies that you could build for your network. And so any self-learning that happened here, eventually it would flood, and when it flooded for the first message, it's going to flood here, here, and a flood message is going to come here. So from the standpoint of switch S4, if A initiated a message, it's going to say, because of that flood message, if I want to reach MAC address A, I'm going to send it out this interface. And so not only can you connect devices to switches, you can connect switches to switches in arbitrary hierarchies and topologies. And typically, it's the practice that you put frequently communicating hosts on the same switch. And so you might have a couple of switches. This might be, say, my research lab, and this might be some of the classrooms. And then this one might be the computer science department. And then this one might aggregate to another switch for some other college of arts and sciences, for example. And so typically you want to associate with the same switch those devices that are frequently communicating, because you don't want to overwhelm, for example, the entire network just because people locally here are talking to one another a lot. And so it's also a traffic shaping strategy, because the better you can isolate your frequently communicating traffic, the more bandwidth you're going to have available to everyone else macroscopically on the network. Okay. Any questions about this? That make sense? Okay. And so this ends our module on networking. And again, project 4.5 is to enjoy spring break. And that is due on Sunday, the 13th, just before midnight, when school starts again on the Monday morning following. So with that, we'll end there, and I'll see you all at 12 noon.